What's up, guys? It's me, Sir Ernest, and today we will discuss a sample problem related to Hamiltonian dynamics. The problem reads: a particle of mass m moves in one dimension under the influence of a force given by this. So that's F, it's a function of x and t, and then that is equal to k over x squared e to the negative t over tau, where k and tau are positive constants. So here we compute the Lagrangian and Hamiltonian functions, compare the Hamiltonian and the total energy, and discuss the conservation of energy for the system. Okay? So we're already given with the force. So therefore from here, we can later calculate the potential energy. Okay? So first we know that the kinetic energy T is equal to 1/2 m x dot squared. Okay, so because here we are told that the particle moves in one dimension, and from the force it is suggested that, or implied that, this direction of the particle's direction is along the x direction or x-axis. So therefore the kinetic energy is given by this. Okay, now on the other hand, the potential energy U, which is given by we know that the force is the gradient, a negative gradient of your potential energy, because the function of the force is along one direction, which is x. So this is now equal to negative partial derivative of u with respect to x. Okay, so now to solve this, we can now rewrite this as an integral equation, wherein du would be equal to negative f dx. Okay, so here we integrate both sides. From this equation, we have negative integral of k over x squared times e to the negative t over tau dx. So here we set that so you notice that as the particle moves away from the origin, the force, or the influence of this force, becomes very, very small. Okay, so that means the potential energy at points far away from the origin will be essentially zero. So that means at x equals to infinity, we know that the potential energy will be equal to zero, and this will be our reference point. Okay, so from here, this enables us to set the following integrals, wherein this integral will be evaluated from infinity to x, and where x is at infinity, the potential energy will be zero, and then we can compute the potential energy at x. So solving this integral, we now have potential energy becomes u, which is a function of x and t, and this is equal to k over x e to the negative t over tau. So therefore, The Lagrangian can now be written as T minus U, which is equal to 1 half m x dot squared minus k over m e to the negative t over tau. So as you will notice that the Lagrangian is a function of x and t, and there's an explicit dependence on time. So this is now our Lagrangian. Now, how about the Hamiltonian? Of course, we need to calculate first the generalized momentum, or generalized momentum in this case because we only have one direction. So generalized momentum. So that is in x. So px will be equal to the partial derivative of L respect to x dot. Okay, so this gives us your usual linear momentum px equal to mx dot, or x dot will be equal to px over m. So therefore, kinetic energy is now written as px squared over 2m. Okay, this means that the Lagrangian in terms of px can now be written as px squared over 2m minus k over x e to the negative t over tau. Okay, so this is the Lagrangian in terms of the generalized momentum and the position x. Okay, so now let's compute for the Hamiltonian. Okay, so the Hamiltonian, so we know that the Hamiltonian will be equal to the sum of p I q I dots minus the Lagrangian for all I. So in this case, we only have one coordinate, so I would be equal to 1. So that's p1, which is our px. So this is now equal to px, and then our qi will be q1, and q1 will be your coordinate x, and then you dot it, then minus L. Okay, so this term will be equal to px times px over m, so that's px squared over 2m, and then this is px squared over m, sorry about that. Okay, and then minus the Lagrangian in terms of px and x, because remember that the Hamiltonian must be a function of position and generalized momentum. So in this case, x and px. So this is our goal. Hamiltonian will be in terms of x and px. So in this case, the Lagrangian in terms of px and x would be this. So this is minus px squared over 2m. So that's minus minus. So this is plus k over x e to the negative t over tau. Okay, so the Hamiltonian will now be equal to px squared over 2m plus k over x e to the negative t over tau. Okay, so now this is our Hamiltonian. So in this case, you will see that the total energy is equal to T plus U. So in this case, T would be Ex squared over 2m plus our potential energy, which is kx, k over x e to the negative t tau. Okay, so you will notice that the Hamiltonian is indeed equal to E plus, is equal to the total energy E, which is equal to T plus U. Okay, so the total energy is equal to the Hamiltonian. Now, looking at the conservation of energy for the system, so you will see that because in this case, the total energy are functions of position, momentum, and time. Because the energy is a function of time, therefore, the total derivative of the total energy with respect to time is not equal to 0. So this means that energy is not conserved. Okay, so that's it. Thank you for watching the video. I hope you learned something today, and I will see you guys in the next video. Bye bye.